Hey everybody, thanks for joining us. I'm Corey and this is Victoria. We are the Professors Du Bois, and today we're going to talk about limiting reactants in chemical reactions. We're going to talk about what the limiting reactant is.
Yeah, and this is a difficult problem for most students. This is something that's kind of challenging, so we want to make sure we go over this in detail, and it may seem like we're going kind of slow, but it's kind of a difficult concept for people to understand. So we're going to start slow and start with an example that you might be able to relate with. Grilled cheese sandwiches. So if you're making grilled cheese sandwiches and you have your bread and your cheese and you're making your sandwiches, we can represent this with a chemical reaction. We can say the bread is our B reactant and the cheese is our C reactant, and we have a 2-to-1 ratio.
So this is not boron and carbon. This is just bread and cheese.
Bread and cheese. And we're making a B2C product. So this is our sandwich. And we're balanced here. We need 2 breads. So we have 2 bread coefficient out here. And we're just going to represent this as our chemical reactions. So the concept of limiting reactant is that one of these reactants will run out. So you may have a truckload of bread, and if you only have 2 pieces of cheese, you can only make 2 sandwiches. And likewise with the other, you can have excess as much cheese as you want, and if you only have 4 pieces of bread, again, you can only make 2 sandwiches. So one will run out, and normally you have excess of the other. And this applies to chemical reactions because it's very, very unlikely that we would add the exact number of molecules of each reactant so that they would stop. There is something that we're going to touch on that we can force a reaction to do that. But in general, if we're mixing 2 reactants together, one will run out and the other will have extra left over.
And once one of your reactants runs out, the reaction stops. We need reactant for it to make a product. So
yeah. So let's say we have 25 pieces of bread and we have 6 pieces of cheese. Right? So since we only have 6 pieces of cheese, we have 1 cheese makes 1 sandwich. That means we have 6 sandwiches that we made. Well, if we made 6 sandwiches, we used 12 pieces of bread. So if we used 12 pieces of bread, we can find out how much excess we have left over. We have 13 pieces of bread left over. So our limiting reactant was our cheese. It limited the reaction. As soon as it was done, as soon as it was gone, it was consumed, it stopped the reaction. So it limited it. That's our limiting reactant. And our excess is our bread. Let's apply this to chemistry here. You want to tuck this?
So we're gonna use a chemical reaction, not bread and cheese. We're gonna use an actual chemical reaction, and we'll have to balance it. And we're gonna use the stoichiometry, like we've been doing, to predict how much product we can make from each of the reactants in the given amounts. And we call that amount of product that we can make a theoretical yield. So what we end up doing is we look at both reactants. There could be more than 2, and we have to see how much product can we make. The one that makes the least amount of product is the one that runs out first. And let's take a look at an actual problem.
Okay.
This will make a little more sense.
We can use particle diagrams to represent this concept of limiting reactants. So here we're talking about actual chemistry here. So hydrogen is light blue, so these are H2 molecules, and the iodine are I2. So we're reacting hydrogen and iodine to make what? So this is one question here down below. What would we make? And it's 1 iodine and 1 hydrogen, so must be we made HI. Okay, and we would balance this equation. If I was writing this, I would balance it with a 2 out in front. So what product is formed? We made HI. How many product molecules are formed? So from this picture, you can look and see, okay, if we have this many molecules of each, how many did we make? We have 1, 2, 3, 4, 5, 6. So we have 6 molecules of HI that were formed. What is the limiting reactant? So you can You can kind of figure that out from how many molecules you made, but you can also see that we have an excess of I2. This is an I2 left over. That means that our hydrogen ran out, so our limiting reactant was our hydrogen.
And you can even see that, there are 3 H2s, or a total of 6 hydrogens, and we made 6 of those HIs with them, and then the hydrogen was gone. And there was enough I2 in there to have some excess.
All right, so here's another example. Ammonia is prepared by the following reaction. We have coefficients. It is balanced. So it says if you mix 10 moles of nitrogen with 25 moles of hydrogen. This is a clue that this is a limiting reactant problem. When you start with amounts, given amounts of both of your reactants, you don't know which one is going to run out first until you calculate it. So that means this is a limiting reactant problem, and we have to figure out which one will run out. That's the question. Which reactant will run out? Which one will make the least?
So we've got 2 reactants. We're going to have 2 calculations to make this determination. We're going to have to look at both.
Yeah. So whichever one makes the least amount of product is your limiting reactant. So with our balanced equation here, we can start with what we know, start with the amount that's given for each reactant and go right to products. How much product can we make? So in this case, we converted moles of nitrogen and we used our balanced equation, our 2 nitrogens, or 1 nitrogen for every 2 ammonias, and we converted into moles of ammonia. Likewise, if we start with our 25 moles of hydrogen, we can calculate how many moles of product can we make. And we realize that the lowest amount of product that can be made was from the hydrogen. So the reaction stops when the hydrogen runs out. It limits the reaction, so the hydrogen is the limiting reactant.
So with that amount of nitrogen, we could have made 20 moles of ammonia. But that won't happen. There's not enough hydrogen to make 20 moles of ammonia. We'll get to 16.7 moles of ammonia, the hydrogen's gone, and the reaction stops. So there will be excess nitrogen.
Yep.
And that's our theoretical yield.
In moles. Oftentimes we ask for theoretical yield in grams, and you'd have to convert that to grams.
So here's another equation, and again, it's got coefficients. It's always good to make sure it's balanced. This one is balanced. And we have 2 reactants, and it says we have 750 grams of each. So we have 2 reactants. We're going to have to do 2 reactions, 2 calculations, and they're both the same amount. So we can go right from grams of ammonia and calculate how much NO we can make, and then we have to do the same thing for the oxygen. The one that makes the least is the limiting reactant. That amount is the theoretical yield. So here's the math kind of worked out for you. We start with the 750 grams of the ammonia, and I use the molar mass to get to moles. That's right from the periodic table. And then I use the mole-mole relationship between the ammonia and the NO, and that came from the balanced equation. So whenever you have mole over mole, we have to use coefficients from a balanced equation to get those numbers. So with the 750 grams of ammonia, we can make 44.04 moles of NO. Now we go to the oxygen, same amount, 750 grams. 1 mole is 32 grams. That's the molar mass of O2. And then next we go from moles of O2 to moles of NO. Again, mole over mole. These are coefficients from the balanced equation. So the 4 is with the NO and 5 with the O2. So 750 grams of oxygen will produce 18.75 moles of NO. That's the smaller amount. That means that O2, oxygen, is the limiting reactant, and we will theoretically make 18.75 moles of NO.
So I oftentimes will just cross out the larger one because I know I can't do any calculations with that. That was something that was fictitious. We can't make 44 moles because we run out of our oxygen. So you go back to the original reactant to say what is the limiting reactant.
That's the limiting reactant. Notice that term, limiting reactant. The answer is going to be a reactant. Sometimes people will write 18.75 mole NO as the limiting reactant, and that is not correct. Now notice at the bottom, we can take that amount in moles and we can convert to grams. This is just using the molar mass of NO. And so that's our theoretical yield in grams.
Yeah, and usually we do want the theoretical yield in grams. But it might say, what's the theoretical yield in moles? And you can just stop there. All right. The next step of this typical problem, the limiting reactant problem, is to say how much excess was left over. How much did you have left over after your reaction was complete? The limiting reactant is gone. You have products only and your excess reactant. So we need to do this calculation in red to be able to figure that out. So the initial was from the problem. They'll tell you how much you have of each reactant. One of them's gone. That's the limiting reactant. So how much was consumed? In order to calculate how much you have left over, you need to know how much was consumed when the limiting reactant ran out. So we're going to start with our limiting reactant because that controls the amount of everything. Once the limiting reactant runs out, we know how much product we can make, theoretical yield, and we know how much of the other reactant was needed to be consumed. So how do we calculate that? We start with a limiting reactant. That controls all of the calculations. We figured out that the O2 was the limiting reactant in the previous example where we showed you all of the calculations. So from there, we're going to go to moles of oxygen, and this is the key here. So on Mole Island, we are going to convert from our initial we're going to start with our limiting reactant of O2 and figure out how much of our other reactant was consumed. So we're going to go from our 4:5 ratio here of oxygen to ammonia. And once we have moles of ammonia, we can go to grams of ammonia, and that's how much was consumed. It might say reacted, how much disappeared, how much whatever. So we can, we know how much we started with. Now we know how much reacted once the oxygen ran out, and this is our excess.
All right, so next up, we've got some practice for you.
Yeah.
And we've got an unbalanced equation, and you're basically posed with all the questions we just covered in this material. So
pause the video and try it out.
Start by balancing that equation, and we'll give you the answers in just a few.
There's your answers. Everything is in red. Your balanced equation's in red. Notice how the answer to the limiting reactant is a reactant. So your answer for a limiting reactant is always something, one or the other, that's on the left-hand side of the arrow. And then your theoretical yield is usually in grams. Notice how we have 3 sig figs for both our answer and the amounts that were given in our problem. And you have your excess.
All right.
So that concludes all of our information on limiting reactants. We hope this was helpful, and we'll catch you next time.
Thanks for tuning in.